Session going, so it's my pleasure to introduce Arnaud Brothier from Rome, who will speak to us on cross products by locally compact groups and intermediate subfactors.
Thank you, Stuart. And I'd like to thank the organizer for putting together a very beautiful workshop in Cambridge. I'm very glad to be here, so thanks for the invitation. And what I'm going to present today is a recent joint work with Rémi Boutonnet. Rémi Boutonnet that we put on archive last year. And it's about subfactors. We will see that what we produce is about infinite index subfactors, but the motivation is actually really started from John's subfactor theory and by certain symmetric enveloping inclusion that you get from classical subfactors, so the symmetric enveloping inclusion that we saw in DIMA talks this morning. So let me just write that the topic is really about action of group G on Q, and what I want is that the relative commutant is trivial, so meaning that I have irreducible subfactors. And what I want to look at here is that I want to look at those kind of cross products where my group G is not discrete but is actually locally compact. So that's really the novelty of this work here. For G locally compact. And one thing we are really interested to, and what I'm going to talk about, is determining what you have between your factor Q and the semi-direct product with respect to your group G. Okay? And the cross product. So we want to kind of determine this lattice of intermediate subfactors that we obtain. Okay. So let me just tell you that there have been some great work that have been done before. So the subject, and I should first talk about the discrete case that has been completely done. So I will remind you more clearly after, but there have been some nice work due to Choda, Izumi-Longo-Popa, and also in the context of compact group and compact quantum group. There's been some nice work of Stefan Bass. And what will be really our setting for this talk is that I will actually ask that my group G is totally disconnected. So that's when we're going to be able to prove something new. Okay? Totally disconnected. And Q is going to be a factor. And actually, for the main theorem, we'll ask that Q is semi-finite. Okay. So it's to 1 or to infinity. Okay, so what I'd like to do first is to begin by telling you what has been done before in greater details. Then I will explain what are the difficulties if you want to jump from the discrete case to the locally compact case, why the situation is analytically more complicated, and what you can do in the totally generally case of locally compact, and then really what additional tool you get in totally disconnected when you get a totally disconnected group. Okay. And if I have more time after that, I'd like to connect this work with classical subfactor theory, so to look at symmetric enveloping algebra, and also action of Hecke pairs of groups. Okay. All right, so let's begin. So let's begin about the previous work. So the first thing, so here the situation is going to be that G is a discrete group, and you let it act on Q, which is a factor, and you want that you still have this condition, okay? which is properly outerness in the discrete case. And so Choda show that so given an intermediate factor like that, okay. So if there exists a conditional expectation, well, you can actually see that n is going to be a semi-direct product with respect to a group. Okay. So if there exists a conditional expectation from the cross product onto n, well then n is isomorphic to Q cross H for a subgroup H inside G. Okay. So if you want to have sort of a Galois correspondence between subgroup of your group G and intermediate subfactor. So your lattice of intermediate subfactor is really simple and very nice. I mean, you can really completely describe it in terms of your group. And the proof is not, it's not very hard, and it can actually be adapted for the locally compact case as well. Okay. So let me just remark that, is that the argument can be adapted for locally compact groups. Okay. But the big mystery is that if I have any intermediate subfactors, I do not know if there is a conditional expectation.
But that you didn't say.
What's that?
So you can adapt it for intermediate subfactors with a conditional expectation.
Yeah, if there is a conditional expectation. So really the hypothesis right here. Yeah. Yeah, excuse me if it was not clear. Yeah. And what is really hard to know if it's really, do we have this conditional expectation? But actually there is a complete answer to this question in this framework for action of discrete group. And this is due to the work of Izumi-Longo and Popa. Okay. So if you have the same hypothesis, you have G which is discrete, and you have an action of Q such that you can see, and then you consider any intermediate from the algebra, so necessarily a factor.
You want compact?
Here I have a discrete group.
No, compact.
No, for discrete. I'm just giving you what's going on for the discrete case, yeah. Well, then there exists a conditional expectation. Okay. And so once you have that, well, using Choda, you can get your Galois correspondence. But what you have also in the compact case, if you're an action of a compact case, you can prove that you have a conditional expectation from Q to any intermediate subfactors between Q and the fixed point with respect to your group G. So putting together Choda plus Izumi-Longo-Popa, well, you obtain that the lattice of intermediate subfactors is completely classified by subgroup. Obtain a description of intermediate
I missed that.
subfactors. Okay. And in terms of close of subgroup of your group G that you started with. Any question, or is it clear? And so another work is that you can do, so I'm going to, here I just want really to do the parallel between, for the cross product action, for intermediate subfactor between Q and the cross product. But you can do another strategy for the compact case, which is with two ingredients, and one ingredient comes for the work of Izumi-Longo-Popa again, is that if you look at group G, which is compact, act in a minimal way, meaning that equal to C, okay? And you consider any n between the fixed point and Q, well then you can do a similar thing. You can obtain that this n has to be the fixed point for a subgroup for G, okay? And then, using the work of Stefan, you can show that you always have that this chain of inclusion is the basic construction for the action of a compact group. And so, just by duality, which is permitted because of that, you can recover the same theorem, but for the compact case. Okay.
G, not K, right?
Yeah, sorry. I was thinking compact and I put some G. Thank you. Okay. And so using this work, you obtain again that any intermediate subfactors between Q and Q times G is of the form N is a Q times H. Okay, and here it's for G compact. All right. So it means that there is already some very nice result in the field, which is that we know it works for the discrete case and as well for the compact case. And I should mention that the work of Stefan here can be also adapted in a more general framework, mainly for compact quantum groups. And you have like a similar correspondence. But here I will really stick to the group case. Okay. All right, so here what we would like to do, so really the question is that given a locally compact group G, that act on a factor Q such that once again we have this hypothesis. So do we have that any intermediate subfactors well is of the form N is a Q times H, okay? So we want to extend to this more general framework. That's really the aim. All right, so I will not give you a complete answer to this question, but I will give you a theorem that gives you necessarily sufficient on your action such that you get such a theorem. Okay. And this provides you a new class of example of non-compact, neither nor discrete action of group when you have this Galois correspondence. All right. So now let's jump to the locally compact setting. Okay, and I will fix a factor Q, a group G, and an action such that we have that. And by the way, this is called a strictly outer action. Strictly outer action. So when you deal with discrete groups, you don't have to be too careful about the definition of strictly outer. Like you can just say that you never get an inner automorphism for a non-trivial group element. When you deal with bigger group, you need to be a bit more careful. Okay, and so as you can see for this correspondence, for the basic construction, which is right here, having this is not equivalent to be strictly outer for in the general case of locally compact groups. Okay, it is for compact group or discrete group, but it is not for locally compact in general. Okay, so what are the technical difficulties that you get when you are in this setting? Well, the first thing is that if we would like to follow the strategy of Izumi-Longo-Popa, well, we'll look at an intermediate subfactors, and we would like to prove that there is a conditional expectation from this guy to this guy. Okay. Well, in general, this conditional expectation will not exist actually. So there is no way to adapt Izumi-Longo-Popa strategy. So I'm not going to mention it in this talk, but we also give a characterization of a subalgebra that do not have a conditional expectation. Okay. So let me just say that in general, there are no conditional expectation from the cross product onto n. Okay. So immediately when you see that, you understand that it's going to be, you will need a different approach in different tools. Also, I should mention is that even more, in general, there is not even an operator value weight. Okay. There are no operator valued weight from your cross product onto n. Yeah. And once again in the paper we give a total characterization of the fact that you get one or not here. All right. And so what does that mean? Well, it means also that you're not going to be able to do some Fourier coefficient and all these Fourier analysis that you can do in the discrete case. Okay. So you get also that there is no Fourier coefficient. So all the classical tools that you would like to use in order to detect what kind of group H you have, to say that your n is Q cross H, well, the first thing you want to do is to look at Fourier coefficient of element of this group. But you cannot do that in a naive way. However, I'm going to show you one notion which is which kind of going to replace this Fourier coefficient, and it's going to be a very nice notion when we look at totally disconnected group. Okay. All right. So let's look. Okay. So let's look at what we got. Well, the main tool we'll be using is something that has been, we kind of rediscover it, but it has been introduced for group from the algebra by MR a long time ago, and it's called the support, and it has been used in a more general framework by Takezaki and Nakagami as well. Okay, so the tool is the support. And what really I should say that in fact it is due to MR and Nakagami, Takezaki. And basically it is what you will expect what it is. So meaning that when you look at an element of the cross product, Q Q times G, you can see it as a function from G to Q. And the support will be just the G's where your function is non-zero. Okay? So I'm saying that if you have an element here, you can say that X is something from G to Q, and you want that the support of X is a set of G such that your Xj is different from 0. And so that's kind of the naive definition. Okay, but it is really what it is here. So inside this phonome algebra, you have a weakly dense subalgebra, which is a set of compactly supported and continuous functions from G to Q, and this is exactly what is the support for them. And so another way to phrase it that was really useful for us, and it's really in the spirit of MR, is the following definition. So once again, I have my element, and I say that the support of X is a set of G such that for any open subset inside G, open and non-empty, well, I have that the projection, and I will in a minute give the definition of those projections. I have that this corner is non-zero, where P omega is just the orthogonal projection from this onto L2 of omega Q. Okay? So when you look at the element of your cross product acting on the L2 function from G to Q, well, you can look at this orthogonal projection, and then you can define this support. As you can see, it makes sense for any operator acting on L2 of GQ. Okay. And what is nice is with this definition is that you can really treat the support as a algebraic relation with respect to your element. And we were able to have a lot of very simple proof, actually, of what we discovered to be some more of them known, but some of them was never written. So it's a bit folklore, but still, it was a good guide for us for going to a partial solution to the question. So let me just give you now what kind of application you can do just by using this notion of support. Okay. Okay. So application of the support. And here, once again, I do not assume that I'm in a totally disconnected situation. I just assume that I have this nice action, which is strictly outer on a factor. Okay. So the main property that we prove, and which will be really crucial in our theorem, is the following. And this property is trivial in the discrete group case, but it is not for locally compact case. Is that if you consider, so if you have an element X in Q times G, and you consider H a subgroup, and moreover you assume that the support of X is inside H, well then you have that X actually belongs to this cross product. Okay. So this kind of sounds completely trivial, but actually it is not here in this context. We really need to work for getting that, and that will be really crucial for what we want to do after. Another thing is that, well, we were wondering actually what is the normalizer of this algebra. So in the discrete case, it's always the unitary of Q cross product G. Here it's not immediate that you get that, but using the support, you can easily show the following, that the normalizer of Q inside the big algebra is what you get in general. So it's a unitary of Q cross product with respect to G. Okay. And so then what you get from this equality is that actually the data, so the data of the inclusion Q inside Q cross G is exactly the cocycle conjugacy class of the action of your group G on Q. So the cocycle conjugacy class that we saw yesterday in the talk of Koichi. Conjugacy class of your action. Okay. So you recover what you want to recover in this context. Okay. And you see that all of that behave very well even in this more general framework. All right. So that was for the really most general case I want to treat. But now I will restrict my group to a totally disconnected group. Are there any questions, or is it clear so far? Okay.
How is this going to cover isomorphic subfactors? I mean, this is just getting subfactors which are exactly equal to the cross.
Yeah, that's right. What will be really useful is the first point. So in the proof, one will consider intermediate subfactors inside Q and the cross product. We'll take an element and we will associate immediately to this intermediate subfactor the group H, which will be just the group elements G, such as UG is in your N, your intermediate. And then all the work will be to show that any element X in this intermediate subfactor will have its support in this specific group H. Okay. So let me just write that very briefly. So later, so the strategy will be the following: is that you will consider intermediate subfactors like that, and immediately you will define the group H being the G in G, so that UG is in N. Okay. And so what we'll do is that we'll consider an element X in N. I want to show that the support of X is in H, is inside. So, and then we use the first point to conclude. But it's really just an additional difficulty because you work with non-discrete group. So this is not immediate, and so you need to do that. Yeah. And those other properties is just to show that everything happens as expected. And the way you can prove it is by using this notion of support, and you get some very easy proof for that. Yeah. This is quite nice. Okay. All right. So for now on, I will suppose that my group G is locally compact, and it admits a compact open subgroup K inside G. So we get something totally disconnected. And so what we want is that we're going to do everything with respect to this subgroup K. That's kind of our philosophy. So locally compact, totally disconnected. And so the idea is to yeah, work relatively with K. And so what happened in this situation? So let me just put some major difference with respect to the arbitrary locally compiled case. Well, the first thing you can see is that the quotient group, the quotient space, G mod K, is discrete. And so it's not a group a priori, but when you see it's discrete, you kind of hope that now you'll be able to do operations that you do in the discrete case. Another thing is that you have now a conditional expectation. So it is not a conditional expectation onto Q, but it's I will write it EK. It's a conditional expectation, sorry, from Q cross G onto Q cross K. So this kind of replace your conditional expectation onto Q in the discrete case. Another thing is that if you want to play on which compact open subgroup K you have inside G, well, it's kind of a very good idea because you will get an approximation of the identity. So you have that the set of K inside G that are compact open, this gives you a basis of neighborhood for your identity element in G. And so what you do is that for a given K, you consider Pk, which is just the integratrix of your group K, and you divide by the R measure of K with respect to G. Okay? And so this gives you a projection in Q times G, and you have that Pk tends to the identity when K goes to the trivial group. Okay? So we get a nice approximation of the identity with those Pk. And another thing is that you have a new description with respect to the conditional expectation for the support of elements that would be more convenient. Is that now, if you consider X in the cross product, you have that the support of X is a set of G in G, such that the conditional expectation EK of UG star X is different from 0 for any of those K that are compact open. And that's really what we're going to use in order to prove our theorem. And let me just put one more thing maybe I will do on the other blackboard. So the last thing is that you get some kind of K Fourier coefficient for X in Q times G, and it's exactly what I did. It means your K Fourier coefficient is this guy, is this EK of UJ star X. Okay. And what happens is that if X has compact support, well then you can write your X as a sum of Fourier coefficient, as in the discrete case. And that's really handy. So you get something like that, where your G mod K in bracket is just a set of representative for this quotient space, right? And so as you can see here, your sum is going to be finite because your support is compact. And so this makes total sense. And it's kind of reminiscent of what you get in the discrete case. If it is not compact, it's not really clear. Sorry, it's not really clear if it is useful to write that. Anyway, it's not going to converge for the L2 nor for the any classical topology, but it will converge to the so-called Burr topology. So, but so far we didn't take this approach, but I believe that's the right way to look at those sums here. Okay, so those are kind of all the handy tools you obtain when you quit the general locally compact case and you arrive to the totally disconnected world. Right. So let me now state the main theorem with the right hypothesis. And you will see that in the hypothesis there is some strong assumption on the action I want to consider. However, there is a lot of action like that, but it's true, it's not the most general type of action that we would like to consider.
Before you erase this, when you wrote n isomorphic to that, you meant equals, it seems to me.
Yeah, yes, that's right, yeah. Yeah, I should say equal, yeah. Yeah, thank you. Yeah, that's true. It's literally the cross product that you see as a subalgebra of Q cross G.
Yeah.
Yeah. Okay. Alors. So let's put the main theorem. So which is Rémi and myself, maybe. So you consider G locally compact, totally disconnected group, and you fix K0 inside G, which is compact open subgroup. Okay. Now you consider Q, which is a semi-finite factor. So in particular, two one factors apply to this theorem. And you have an action, sigma, which is from G to Q. And I'm going to just put the name of this kind of action and then give you the definition, which is properly outer with respect to K0, my subgroup, and which is minimal when restricted to K0. And such that sigma restrict to K0 is minimal. Okay? And so in that case, we get exactly the conclusion we would like. So then, given an intermediate subfactors, there exists a subgroup H side G such that, and then you're right, I should really put equality such that my n is equal to my Q times H. Okay. And before I give you the definition of this funny action, let me just give you one set of example.
The action is simply trace preserving?
No. No. And so an example will be given by some Bernoulli action. Okay? And this time it's going to be trace preserving, where Q02 is a 2-1 factor. Okay. So when you shift bar Bernoulli, but you do it modulo your subgroups, right? And you start with a nice action Q0 with respect to K0, where you get what you want. Okay. And you can also do it for a free product of those K0. Okay. And it works for free product, free Bernoulli, I should say. Okay. So we kind of show you that there are some natural actions that arise in this way, that satisfy the assumption of the theorem. But let me just give you now the definition of this proper outerness with respect to the subgroup. Okay. So as before, we have the same thing, K0 and G. G action K is properly outer with respect to K0 if, well, you want to look at what kind of element can intertwine your action, but with respect to the K0 fixed point. So that's the difference with the proper outerness. So you look at the set of G in G, such that there exists an element in Q, which is different from 0, such that it implements the action for a given group element G, but this time for only elements that are already fixed for K0. Okay? So you look at this set, and you want that this set is the smallest that it could be, meaning it's K0. Okay. And so one remark is that if I state this for the trivial subgroup, well then, and call my action sigma, then sigma is just properly outer. Okay? So once again, I was saying that the philosophy here for our work is to do everything with respect to a compact open subgroup, and so you can also see it in the hypothesis of the main theorem. Okay. Okay, so I don't want to spend too much time on the proof, because I basically show you what are the main difference and what kind of tool we have. I will just tell you briefly what we do. So as I was saying, the proof is in 2 steps. And the first step is to define this subgroup H of G with respect to intermediate subfactors. And all the work after that is to show that the support of any element in N is going to be in H. Okay. So the strategy of the proof, as I wrote before, is you consider your N, you define your H, that are the elements such that UG is in N. And so immediately you get that QCM cross product H is inside N. And what you want now is to show the other implication. Yeah. So you want to show that N is inside H. And to do that, what you do, you consider your element in N, and you want to show the support is inside H. And the starting point is to consider a group element in the support. And so for k small enough, you will get that this element is going to be different from 0. Okay. And what you do is that you do some averaging arguments on this element, and you obtain something that will commute with a fixed point of k with respect to k. So for that, you obtain something in here. And you work a little bit more, and you obtain that your G is actually an element of H necessarily. Okay, so that's really brief, but yeah, I don't want to become too technical also. All right. So that's the main theorem. Well, since I have like a bit more than 10 minutes, I just want to talk about a slightly different theorem that we have been doing, which is really less technical, but it's connected in a sense to subfactor theory. So let me maybe start with subfactors. And when I say subfactors, I mean classical subfactors of finite index here. Okay. So when you consider a graph, a bipartite graph with nice properties and a weight on it, and consider an action which is vertex transitive, if you have the right hypothesis, you can build from that a subfactor planar algebra. Algebra, if you write P. And this subfactors planar algebra contains some information about your group action. And what you get is that the symmetric homopy inclusion so T of inside S that we saw in Dimas' talk, can be sort of described actually via this group G and this action of gamma. So what do I mean by that? Well, you can consider, so let me just, it's going to be, I'm not going to give all the definition, but I just want to show you how it's kind of related to subfactor theory. So you pick a vertex in your graph, okay? And you consider your GV, which is a group element that fixes this vertex. And what you get is that this inclusion is really nice. It's actually what is called almost normal subgroup. Okay. Or also called a Hecke pair. Hecke pair. So what does that mean? Well, it means that for any S in G, you have that this group GV intersect the translate like that as finite index in both G, what I'm doing, in both GV and the translated. Okay. And once you do that, you can actually make sense of a convolution algebra for a function that goes from G to the complex number. Okay. So you can consider the set of functions, and here I can put a target algebra A, such that you have a relation like that, yeah, for Hk in the small group and G in the big group. Okay, when you have an action, G on A. Okay, and so there is a way of taking a completion of this convoluting algebra, which is really, you should think of a group, a semi-direct product of a fundamental algebra with respect to a Hecke pair. Okay, so you get some kind of cross product of a fundamental algebra A with respect to this Hecke pair. Okay. Okay, so let's write it like that. Okay. And so what happens is that you can show that your S is actually isomorphic to such a cross product. Okay. But what we saw is that actually this thing is nothing else than a cut down, a corner of a semi-direct product with respect to my group G, my big group G. So this is PEV of A times my group G times PGV. Okay. And so what you have here is that your pair GV inside G is my K inside G. Okay. So what do I mean is that this symmetric enveloping algebra also in Popa that you obtain, that is given from a subfactors or a planar algebra, is actually a cut down of an action of a totally disconnected group. And this was the original motivation for Rémi and I to investigate those actions of totally disconnected group. Okay. And another thing is that basically because of this correspondence, you can have a similar Galois theory theorem with respect to subalgebra of this algebra. Okay. So what I'm meaning is that you can get a Galois correspondence for the Hecke pair context as well. Right. Okay. Well, I think I will stop here. Thank you.
Questions, comments?
Does the probability play any role in your results?
Actually, we don't need a separability. Yeah. So the nice thing is that it can be very general for that, neither for the group and neither for the fundamental algebra. Yeah. We never need to assume that we have a state also. So, yeah.
Any other questions? If not, let's thank Arnaud again. With thanks to Arnaud.